On Friday, we talked about 2 different ways to find the empirical formula, and to then go to the molecular formula. Now we're going to talk about it in reverse. If you first find the molecular formula, it's very simple to find the empirical formula, because an empirical formula is just a reduced molecular formula. So if you first find the molecular formula, you reduce it. Now you have the empirical formula. So if you want to do it that way, using the example from the previous page, I have a molar mass of 256. We're going to assume we have 1 mole. For an empirical formula, we assumed we had 100 grams. For a molecular formula, we're going to assume we have 1 mole. That's going to be the difference here. Everything else is basically the same. So if I assume I have 1 mole, and I just said that the molar mass is 256 grams per mole, then I have 256 grams. In the given problem, up here at the top, I was given percents for each element. 65.6 C, 9.44 H. My percents will add up to 100, and therefore I can find 9% of oxygen. So given each one of these percents, I do my percent times the mass to get 167.9 grams of carbon, 24.2 grams of hydrogen, and 63.9 grams of oxygen. I have grams. The only unit grams can convert to is moles. There is no other option. When you're at grams, if you look at the mole map, or if you think about units for grams, the only thing that grams can be converted to is moles. Therefore, we convert to moles. 167.9 grams of carbon, using my molar mass, to find I have 13.98 moles of carbon. 24.2 grams of hydrogen. Notice this is hydrogen inside another compound, so we're not talking about H2. Hydrogen by itself is diatomic and hangs out as H2 and has a molar mass of 2.016. In this case, when it's inside a compound, I'm only talking about 1 atom. For each 1 mole of this entire compound, I'm talking about the 1 hydrogen in there, so therefore it has the mass of 1.01. Be very careful when you're dealing with those diatomic molecules. Is it the atom by itself inside a compound? If it's an atom, it just has the molar mass on the periodic table. If it is a molecule, if I say oxygen gas, hydrogen gas, those things by themselves, they have the 2, that diatomic 2, and the mass corresponds to that. All right, just a mistake I've been seeing, so I want to point that out. Now I have my moles of hydrogen, and I go from my grams of oxygen to, once again, my moles of just oxygen, not oxygen gas, not the molecule, just oxygen. So in this compound, these are my ratio of carbon to hydrogen to oxygen. And I want a whole number ratio. Now 0.98, 0.96, and 0.99, it's going to be very difficult to find something to multiply each one of these by to get to a whole number, but when you look at it, all of them round to a whole number. We're so statistically insignificant away from that whole number, we can round. Now that is important. You can only round when you're really, really close. So if 0.5, 0.33 repeating, or 0.66 repeating, those are going to be the common ones you're going to see that are multiplied. Okay, if it's 0.5, you multiply by 2. 0.33, multiply by 3, right? That's how you're going to get that whole number ratio. If you end up with something that's a 0.81, that's not going to happen. Okay? Now, in nature, in a very high-level lab, you might see that, but nobody's going to give you a question with a decimal of 0.81. The only decimals you should be seeing are a 0.5, 0.33, or 0.66. If you have a 0.81, you already know you've messed up. Go back and fix it. Okay, you should be able to easily round to a whole number or easily multiply by a small whole number. We're not talking about multiply everything by 19.2, and now we have a whole number. Okay? So once we have this and we round it up, then I end up with my molecular formula of C14H24O4. I know this is a molecular formula because it's not simplified. If I take this molecular formula and I simplify it from here, I get C7H12O2, and that would be my empirical formula. Hydrates are when I have a compound that has water attached to it. I'm not talking about chemically bonded to it. I mean in a process of crystallizing, these water molecules are stuck in the crystal. They're just attached to it. It's not a chemical compound. As soon as you add it to water, or as soon as you start heating it up, they separate. They're not even attracted to one another. Just in the crystallization process, they get stuck in that crystal. So these are going to be very common on the AP exam, so we want to make sure we know what it is we're talking about when we see hydrate, and we know this ratio. So when we talk about a hydrate, we use a dot to state how many water molecules are attached. Remember, it's the word attached, not chemically combined, to the crystal. So the most common one we will use, and we use this in pretty much, I think it's 5 of the 20 labs we do, will all use this compound. Copper 2 sulfate pentahydrate. If you were in my class last year, we used it. It's those pretty blue crystals. Okay. So how do we name these? Well, water is a covalent compound, so it uses covalent naming. We're going to use the word hydrate, and we use a prefix for the amount. So the prefix is mono, di, tri. Okay. So my most common example will be the copper 2 sulfate pentahydrate. It's a real pretty blue crystal because the copper ion's blue, and so when they crystallize it, you get those pretty blue crystals. All right, so when it's anhydrous, we're talking about the part that is without water, because An is a negative, hydra meaning water, so without water. So usually the problem is going to help you determine the grams of water, and then you're going to find that ratio between the two. So once I have grams of each, both the water and of the anhydrous, of the compound that the water is attached to, then I'm just going to follow the steps to find empirical formula. Once again, I'm looking for the simplest ratio, but this time instead of the simplest ratio of atoms, I'm looking for the simplest ratio of how many of these to how many of these. How many crystals, how many of that compound per how many waters. So in this example, I have 1.357 grams of copper or cobalt 2 chloride times, and we don't know how many waters. We're just told that this is a hydrate. They give you these crystals. I don't know how many waters are in there. That's very important if you're going to do your lab or you're making a solution. I have to know how many grams of cobalt 2 chloride am I actually using, because the grams of water is going to entirely affect the weight of that crystal. So if I have a 1.357 grams of the crystal and I heat it, that water will immediately go away. Right? As you heat it and it melts down, that water will go away, and all that's left is 1.062 grams of cobalt 2 chloride. So then I need to find that ratio, find my x. Well, I subtract and find that I have 0.295 grams of water, and I was given that I have 1.062 grams of cobalt 2 chloride. So instead of going all the way down to the atoms, my simplest ratio is just the ratio of cobalt 2 chloride via water. So we do our empirical formula, the same concept. Start with my grams of the compound, convert to moles. Start with my grams of the compound, convert to moles, because if I'm looking for a ratio, it has to be a mole ratio. We don't talk about gram ratios. We talk about mole ratios. In order to find a smallest whole number ratio, once again, you divide by the smallest. If I divide by the smallest, I end up with 2 waters for every 1 cobalt 2 chloride. So then my formula is cobalt 2 chloride with my little dot. For every 1 of those, I have 2 waters. For concentration, when we're talking about concentration, we're always talking about a relationship of solute to solvent. Solute is dissolved, solvent does the dissolving. So the solute is always going to be the smaller amount. It's the thing that's going into the larger amount. There are several ways to talk about concentration. Obviously, the most common is going to be molarity, and that's the last one we'll talk about. We'll use that pretty much daily throughout the year. Okay, but there are other ways, and we're going to briefly cover those, such as percentages. There are 4 percentages that use concentration. We'll look at the next page. We have percent by mass, percent by volume, and percent mass. Now, all of these are percents, and I told you when you're talking about percentages, instead of memorizing each equation for each type of percent, wherever we're going to talk about, it's always just consider it as part over whole times 100. The name of the percent should tell you what your part is and what your whole is. So percent by mass, well, we're talking about mass, so we have gram and gram. The part is going to be the solute. And the whole thing is the solution, the entire thing together. Part over whole. So grams of solute over grams of solution. You don't need to memorize that. The name should tell it to you. If it's a percent, it's always part over whole. Percent by mass, use grams. Okay. Percent by volume. Milliliters of solute over the whole. Milliliters of solution. And then percent mass, and sometimes referred to as percent mass volume, would be grams per volume. So the name should give it to you. And every once in a while, one of these will pop up on the AP test, or you'll pop up on a quiz. But I don't expect you to have it memorized. I expect you to be able to logic it, based off of the information given and the name of the thing that's being asked for. You should be able to figure it out. Now, sometimes these percentages will come in ppm, which you probably have seen before as parts per million, parts per billion, or parts per trillion. We will be working in parts per million a few times this year. We don't have anything that's in parts per billion or trillion. Now, another common way is going to be to use mole fractions. So a mole fraction, a mole ratio, and molarity is all using moles, not milliliters, liters, or grams. We're all talking about moles. A mole fraction is moles of a substance over a moles of everything, because it's a fraction. A fraction is always that part over the whole. That versus a ratio, I'm going to make this darker, moles of substance over that. A ratio is always comparing one to everything else. So a mole ratio is moles of one thing versus the moles of everything else. So you use that terminology the same way you use it in math class, of a fraction versus a ratio. If you haven't ever considered that, that's the difference between a fraction and a ratio. A ratio is comparing one thing versus everything else. And then we have molarity. The most important and most common thing we will talk about in this course. Molarity, moles per liter. Okay, molarity, mole liter. Moles per liter. It's not milliliter. It must be liter. Okay. You will see millimoles at some point in the year, and millimoles have to do with milliliters. But we're talking about molarity. Okay. So molarity uses this capital M for its symbol. But that capital M, if you're ever doing stoichiometry or you need to put it in dimensional analysis, you're always going to actually convert it down to MOL over L. Moles per liter. Molarity is moles per liter. So make sure those two are synonymous in your brain. If you see something as moles per liter, that means molarity. But instead of saying the word molarity all the time, we normally talk about molar concentration. So I say I have a 3 molar HCl. Okay, that concentration is very important, especially when we're talking about acids. Now, being able to convert this capital M into mole over liter is important for the stoichiometry. Because if I give you 0.5 M, and you start with 0.5 capital M on top, there's nowhere to convert. Capital M doesn't convert to anything. However, if I put the mole and I put the liter, both of these can convert to other things. Okay? So make sure you're able to follow this part. If you have that capital M, switch it up when you're putting it into stoichiometry. That way, look how I'm able to cancel out my moles, and I can end up with moles of Cl over liters because my moles canceled out and I switched to a different ion. So stoichiometry, the definition of it is going to be the study of the quantitative relationship between amount of reactants and products. Okay, we're looking at that equation. We're going to look at a simple graphical approach to this, a visual representation to make sure you don't mess up each of the steps in the stoichiometry. Stoichiometry as a whole is very simple. Most people can understand it. There's just a lot of simple mistakes that are made along the way, so I'm going to try and prevent those. The way we're going to prevent those is anytime you're given an equation, you're going to follow these steps. First, you have the balanced equation. If it's not balanced, it's useless in my class. You need to balance the equation. Then under that, you're going to draw two lines. 1, 2. On this first line, you're only going to ever put moles. Don't ever put anything else. Oop, that's a weird arrow. Okay, don't ever put anything else on that first line. Only moles. On this second, below here at the bottom, you're going to put everything that can convert to moles. Anything else? Representative particles, liters, grams, anything that can convert to moles goes on this bottom part. When you're in this moles area, you can only go left and right. From moles, you can only go to moles of something else. When you're in this bottom area, you can only go up and down. You can only go from something that can be converted into moles to moles, or back down. I've got several examples of this. Anything you're given, you'll mark that in the correct location. If I'm given moles of O2, it'll go in the moles line right under O2. If I'm given grams of O2, it'll go at the everything else line below O2. If I'm given liters, representative particles, anything like that, that'll go down here. Then we can follow a path to figure out where we're going. So let's look at an example of this. 150 grams of titanium 4 oxide is reacted with bromine trifluoride. Find the number of liters of oxygen gas at STP, the number of molecules of bromine, the number of moles of titanium 4 fluoride, and the grams of bromine trifluoride required for the complete reaction. This is several parts. And now on an AP question, it wouldn't all be listed in that. It'd be like have several little I's, find each one of these. But for now, make sure you're looking at this. So my first step is to have an equation, but it has to be a balanced equation. Okay, so let's go through, and I'm going to go all the way through all the steps with this one because I had a couple people struggling with balancing on a more complicated question. So if I have 1 Ti, 1 Ti, 2 O's, 2 O's, 1 bromine, 2 bromines. Now before you go to fix this bromine, notice how bromine is by itself? This will be the easiest to fix later. Go check and see if anything else will be more complicated. Come back for any elements that are by themselves, balance them last. That'll make your life a lot easier. So then I look at my fluorines and I have 3 and 4. That's more complicated to fix. My least common multiple for them will be 12, so I can just switch them. If I have a 4 here and a 3 here, my fluorines are fixed. I have 12 of each. Now let's start checking everything again. 1 Ti, 3 Ti's. Nope, gotta fix it. Okay. 3 Ti, 3 Ti. 6 O, 2 O. Gotta fix it. 3 Ti, 3 Ti, 6 O, 6 O. 4 Br, 2 Br. 4 Br, 4 Br. 12F, 12F. Notice I go back and double check anything that I've changed. Okay, I see many people, they'll fix one thing, but when they change something else, it messes it up. Got to make sure you go through and check them all. This is officially balanced. I put what I was given, 150 grams of titanium 4 oxide, in the non-mole area. Only moles can go in this line. Goes in the non-mole area below what it is. I put a question mark for everything I'm looking for. And then I will draw arrows to help me figure out how many steps do I need to solve each one of these and what conversions will I need. So let's look at the first one on the next page. So if I first want to solve for molecules of bromine, I just draw my arrows. If I'm at grams, if I'm at anything in this bottom line, I have to go up to moles. Okay. Go from grams here to moles. Okay. So I have to use a gram to mole conversion. Once I'm in the mole line, I can go anywhere else in the mole line. I can go from moles of titanium 4 oxide to moles of bromine. using my molar ratio. Once I'm at moles of bromine, then I can go to anything that moles converts to. I want molecules. That goes down here. The number of arrows is how many conversions you must have. If you have fewer or more, you've messed up. 1, 2, 3. I'm required to have 3 conversions here. If I put this in stoichiometry, grams to mole, use the periodic table. Mole to mole, use my balanced equation. For every 3 titanium 4 oxides that combust and go through this reaction, I produce 2 bromines, 2 molecules of bromine. So for every 3 of these, it will be producing 2 bromine. Now I'm in moles of bromine. Moles of bromine, go to molecules of bromine. And I have my answer, which is molecules, Br2. If you put molecules of Br, you would be wrong. There is no such thing as a molecule of Br. A molecule is something with 1 or more atoms, or 2 or more atoms. So a molecule of Br does not exist, and Br is not what the question was asking for. It was asking for bromine by itself, which is diatomic. It must be Br2. Okay. There's an example for each kind. If I want to go from grams of one substance to grams of another, that's 3 arrows. Up to moles, mole to mole, down to grams. If I want to go from grams of one substance to moles of another, that's 2 steps. Gram to mole, mole to mole. However many arrows there are, that's how many steps you need. Each type of conversion you would need. Don't forget, when you're going to liters, it needs to be at STP, and it needs to be a gas. So one of your diatomics or a noble gas. Go look at practice problem 1 now and complete it.